having just 45 minutes. Okay, fine. I'm going to start today's lecture. Okay. So today we will discuss about today it is lecture number 27. So we will discuss about orthogonal projection and orthogonal complement apart from orthogonal basis. Orthogonal or more importantly orthonormal basis, and with respect to orthonormal basis, we will define the concept of inner product. That means dot product, to what you have already gone through in high school. So I will give a general idea of inner product. General idea of inner product or orthogonal projection from our model last model, previous model, and I will talk about its geometry and its relation with the orthonormal basis. Then I will give with the help of this orthonormal projection, call it always orthonormal. So there is no much difference between orthonormal and orthogonal. Difference is that one is orthonormal set of vector. It happens to be unit vector. Every vector happens to be unit, and orthogonal it is not unit criteria is not there. Every vector are perpendicular to each other vector in this orthonormal basis. And in orthonormal, apart from with canonical or standard basis, another name of basis, you can call it E, having basis vector E1. E1 means what? First coordinate is 1 and others rest of coordinate are 0. All these are 0. Just this one is 1. And E2 means second coordinate is 1 and rest of coordinate are 0. Rest of coordinate is 0. So if you take any general vector, combination of these basis, a standard basis vector E1, E2. So you can, so suppose you are having a vector with coordinate x1, x2, xn. So simply you can say that x can be written, actually this x is written as x1 time E1 first basis vector plus x2 time E2, likewise plus xn times E1. So if I am asking what is the coordinate of given vector x with respect to C, coordinate is x. The coordinate relation, that's way there is no different representation of coordinate vector in case of standard basis. There is no, so because coordinate factor of a vector with respect to representation. Now we will see here few properties of basis element and basis element of a standard basis. What are those properties? First properties, if you take inner product of, you might be aware of inner product. Inner product, it is talking about dot product. Just seen, so it is talking about component wise multiplication of coordinate and further sum it up to last. xn yn. So this one is obvious kind of inner product. But remember that whenever you are defining inner product of any two vector in Rn and dimensional space Rn, then you are talking about basis. So inner product is also dependent on basis. Till now we had already seen that coordinate of a vector always it is dependent on a basis. So you always demand that if I am asking saying that this one is a vector, then your next question would be what is the coordinate vector of that vector. So coordinate vector with respect to which basis. Next, we have already discussed about linear transformation. So if you are trying to find matrix of that linear transformation, then like here. So we are defining inner product of x and y with respect to basis like respect to itself, and what would be. So in another way of inner product also you can represent it like in linear algebra. This representation is very interesting because it is talking about projection approach, and inner product is also representing physical geometrical one geometrical meaning of inner project. It is talking about the projection. So that's why in linear algebra we will be more y. That means here don't confuse mix it with x into y transpose. It is outer product. This one is outer product of any two vector with respect to astral basis E. We call it x into y transpose because it would be a matrix. It will give a matrix. It will not give a number. And this one is inner product of xy with respect to basis, standard basis E. And with respect to a specific basis, we need to know what is the basis, and then we will talk about the representation of few concepts. So it is inner product of xy with respect to basis E. Standard basis. So if you take inner product of jth element of this standard basis with respect to itself, then what would be? It would be 1, 0 with find the dot product of 1, 0 with 1, 0 itself. What would be this one? So do a component wise multiplication, then sum it up. Then that means 1 times 1 equal to 1, and 0 plus 0 times 0 equal to 0. So 1 plus 0, it would be 1 plus 0 is what? 1. So you can see that it was what? E1 in R2, and this one was E1 in R2. So E1 dot E1, it is equal to 1. If you take E1 dot E2, the product would be 0. Inner product would be 0. So multiply inner product, it would be 0, 1. So that means 1 times 0 plus 1 times 0 is 0, and 0 times 1 is again 0. So 0 plus 0 equal to 0. That means inner product of 1, 0 and 0, 2 is. So it is perpendicular nature. When inner product happens to be equal to with respect to the corresponding basis. So this here you can observe like that way. So in general, if you take any j basis vector from external basis, if you take define inner product of these two, what would be this called delta? This we are calling it chronicle delta. It is very a specific word in easy many branches you might have already seen that. So chronicle delta is taking value 1 when I j equal to k and I think Einstein might have used this notation. This one is very interesting kind of notation. So inner product of uh, basis element of a standard basis, you can always represent a chronicle delta. So next we will talk about arbitrary vector xy from Rn, and we have the following representation of xy with respect to a standard basis E. So if you are taking x, then x and that means x is a linear combination of uh, this basis, a standard basis element E1, E2, E3. So that's why we are saying the coordinate of x with respect to a standard basis is the vector itself. Similarly, if you take another vector y from Rn, then you can say that y can be represented as a linear combination of a standard basis. This is a linear combination, and it simply says that coordinate of y with respect to basis is the vector itself. This one is Rn. Everything is happening in Rn with respect to a standard basis. Now, when I am asking that what is meaning of this coefficient, how can you directly calculate this coefficient? So what you do, take x and take any basis element E1, any E1, E2, whatever you want to take. So I have to, for simplicity, I have taken E1. So take inner product of x with E1. So what does it mean? So x just translate in the term of basis vector and take inner product with E1. Then it will take so it is defined component wise addition. So inner product of first component of last component with E1, and we know that here x1 is a scalar. It will come out, and here what would be simply you can write it E1 times inner product of E1 with E1, and we know that if what is the inner product of E1 with itself? It is 1. So that's way this term would be, first term would be x1, and second term onward would be 0, because second term it will involve a dot product of E1 E2 with E1, and E2 E1. So that's where this dot product or inner product would be 0. So last term, this nth term also it becomes 0. So that's where we are. This is E1. Then you are getting, you can get second coordinate. So if I'm of the vector, you can say that inner product of the inner product I j equal to k, otherwise it would be 0. So that's why this scenario is coming here. Diagonal scenario will come here when j equal to k. Anyone is having any doubt? So it looks that I have to go forward. So here I will talk about few properties of inner product with respect to a standard basis within a space Rn. So we have already seen that inner product of any two vector x, arbitrary vector xy with respect to a standard basis, it was defined as a sum of component wise product. Sum of component wise product. This one is already you are familiar with. It is having following property. First property it is talking about inner product is always symmetry. So that means order is not matter here. So if you take dot product to or inner product with x with y, that would be equal to inner product of y with x. So proof is very simple. Why proof you want to see? Just use this definition. We know that xj, yj both are a scalar. So this simply you can say that a scalar multiplication also you can write it. A scalar multiplication is always commutable because one into two equal to two into one, and two into three equal to three into two. So always a scalar multiplication of multiplication of a scalar number is always commutative. So from there you can derive that inner product of any two vector with respect to a standard basis is always uh, commutative or symmetric. Similarly, you can also establish so this task you can take as a homework. So inner product of any two vector x, y, if you take, then it is again satisfying linearity property. That means if you find inner product mm, of this one, alpha alpha x plus beta y with z, it would be what? Inner product of xj, alpha times inner product of xj, and plus beta times inner product of y with z. Inner product of x with z and inner product of y with z. So linearity is you can see that linearity is just it is of the linearity. So this operation is also very much interesting. You can all these property you can prove from this definition itself. So easily you can prove this definition. So remember that whenever I am asking what is the inner product of two vector and you are defining like this way, it simply says that you are defining inner product with respect to this standard basis E. Now, last property, this one is very important and very, it finds it is changing with respect to different kind of inner product. So you have to very much focus over this inner product. What does say? It is talking about positive definiteness. That means if you are taking any non-zero, if you are taking any vector, then inner product of any vector with itself, it is always greater than equal to 0. And this inner product will be 0 only in case when the vector is 0. So this criteria. So that means this inner product of a vector with itself is greater than 0 for every non-zero vector in Rn. For every non-zero vector in Rn, it is greater than, strictly greater than 0. And inner product would be 0 only in case when your vector is 0. So inner product of vector x with itself is 0 in only case when your vector x is 0 vector. So only 0 vector is having 0 inner product. So in layman way we can say that if you are taking any non-zero vector, that inner product of non-zero vector with itself, it will be always a positive number. And if you vector, then inner product of 0 vector with itself is always a 0 vector. So these three properties are very important for inner product. Now, based on that idea of a standard basis, we will define orthonormal basis of Euclidean space Rn. So how can we define? So suppose we are having an orthonormal basis Rn with basis v1, v2, vn. So you can see it here. Representation has been changed. I'm not taking E1, E2, E3 kind of.
Sir, your presentation is not visible.
Okay, not visible.
No, sir.
Okay, I will see it. Is it visible?
No, sir.
Not visible. Just see it again. I shared it.
Yes,
Is
sir.
it
Yes.
visible?
Now it's visible.
Okay. There might be some network issue. That's way. It's fine. Whenever you face any problem, let me know. So I'm going forward.
Sir, we are able to see. We are not able to see this. Yes, sir. It's visible.
Other. Okay. Fine. So I'm going forward. So we are taking a basis other than a standard basis, but other than a standard basis, that means you can simply say that we are taking a non-standard basis. So this non-standard basis, and it is a this O is a non-standard basis, but again we
Sir,
want
again it stopped.
orthonormality.
Sir, it stopped
again, sir.
What is happening? I have already shared it.
Sir, after you shared, it stopped again.
Now, is it visible?
No, sir. Yes, sir. Yes, sir.
No. Okay, fine. So what we observe it here. So here we are taking a non-standard basis. O is a non-standard basis. That means our basis element are no more E1, E2, E3, A, or like En kind of things. So we are having a non-standard basis O in such a way the basis elements is satisfying the similar property what a standard basis element had. So like that means if you find a inner product of Vj with Vj itself, it is 1. And that means it simply say that norm of Vj is 1. And if you take inner product of Vj with other element Vk, basis element Vk, and that one is 0. So what a standard basis had? So a standard basis had a property that inner product of Ej with Ej itself, it was 1. That means unit vector property, and inner product of Ej with Ek, where j is not equal to k, we had 0. Inner product was 0. So similar feature we observe in this non-standard basis as well. Then such kind of basis we are calling it a orthonormal basis of the given vector space or linear space Rn. So that means we say that here inner product of Vj with Vk also we can define with the help of chronicle delta. We are defining with the help of chronicle delta. But these VIs are not EIs. These are other than VIs. I will take few example here. So one simplest example, what you do. So this one is orthogonal basis, but O1 is orthogonal basis, but O2 is orthonormal because basis element of O1 would be 1. It would be root 2. Like, but if you see in O2 norm of this V1 would be 1 and norm of V2 would be 1 again. So it is all just related with normalization. So what we do? So see here. So first we will see property whether O1, what are the property of basis element of O1. So inner product of V1 with itself in O2 with itself. That means you are talking about inner product of 1 by root 2, 1 by root 2. 1 by root 2, 1 by itself. 1 by root 2, one by root 2. So what would be inner product? Here we are finding inner product with respect to right now find a standard basis. So what would be inner product? 1 by root 2 times second component of V1 is 1 by root 2 with multiply with 1 by root 2, that would be again 1 by. Now take inner product of V1 with V2. What would be that? So directly I am defining it. Multiply with minus 1 by root 2 first component. Second component you will get it from 1 by root 2 multiplied with 1 by root 2. So that means minus. So what is summation? Summation is 0. So inner product of V1 with V2 in O2, what we observe 0, and inner product with itself is 1. So you can say that here O2 is a R2, Euclidean space R2, orthonormal basis. Similarly, this one is also, it is, so you can say that it is orthonormal B. So O2 is a orthonormal basis of R2, and this one is a what orthogonal basis of R2 because V1 is not having unit law. Orthogonal, so OG to B. So O2 is a orthonormal set of vector, and O1 is a orthogonal set of vector, and these two are also forming basis of R2. But this O2 is very close to standard basis E. What is the standard basis here in R2? Standard basis is 1, 0 and 0, 1. So whatever feature we observe in standard basis of R2, similar feature we also observe there in O2 as well. Similar feature we observe. Just coordinate will be changed. Another example also, if you take any two-dimensional vector space V from C infinity, and if you take a basis having first element cosine of x, second element sine of x, then what you observe? This spaces also form a orthonormal basis of this subspace in C infinity, two-dimensional subspace in C infinity. How? You know that if you find dot product, what would be dot product? So dot product of cosine with itself would be 1. Now your question would be how we define dot product of two functions. So it is a function kind of things. So function we define with respect to integral. So that means you are integrating this one in the what is the period of cosine x? It is 2 pi. So integrate in the interval of 2 pi, or you can simply say that you can interval minus pi to pi. Also length of minus pi to pi interval is also 2 pi. So integrate this one with respect to x in interval minus pi to pi of cosine x. That cos x into cos x, that means cos square x. You can find the integral of this one, what it would be? It would be 0. No, it would be 1. You can calculate, this one is a homework, you can calculate integral of this one would be 1. Cos x into cos x means cos square x. Similarly, inner product of cos x with sin x, it would be 0. Cos x with sin x. So it is all about idea of high school. Just you change your mind, whatever you have studied regarding orthonormal standard basis, you are just trying to change it to non-standard basis, which are having similar feature what standard basis is having. So here, if you find dot product of cos x with sin x, it would be 0. That means it is equivalent to finding integral of product of cos x and sin x in the interval minus pi to pi, that would be 0. You can easily verify that. So this one is forming cos x and sin x is forming vector space of C into V. I had given name. This one was Fourier space. That means if you take any as a summation of sine and cosine. So this V is a Fourier space. I will discuss later in detail further. In application part, I will discuss in detail. So this one is your Fourier space. So Fourier space is having orthonormal basis, cosine x and sin x. That one is similar to standard basis. Now we will try to look more about orthonormal basis of Euclidean space Rn and inner product. So if you take any two arbitrary vector from Rn, then we can see the following properties. So that means if you are taking x and y, any two arbitrary, and you now your two non-standard basis, that one is orthonormal in nature, but means it is non-standard but having the same feature what E is having, a standard basis having. So we first task would be what is the coordinate of a given vector with respect to a standard basis O. So coordinate is coming like this way. Coordinate, how we are getting it, I had already discussed several times. Either you go for change of basis metric approach, or you go for solving system of linear equation. That means express the given vector x as a linear combination of the basis vectors, and then find the corresponding coefficient by solving the corresponding system of equation, like capital V times alpha equal to x. You have to solve this system of equation. Then you will come across to know what are this coefficient alpha is. And once you are getting those coefficients, those put as a make a column vector. That vector we are calling it vector of the given vector x with respect to a standard basis. Similarly, coordinate vector of y with respect to an standard basis with respect to that orthonormal basis is this one here, because y is different than x. So definitely coordinate vector of y would be different from coordinate vector of x. So we are getting coordinate vector of x and y with respect to a standard basis, and you are already aware of these representations. So we will talk about first what are these coordinate vector can we directly find with the help of inner product. Yes, we can find. So what you do, so do a dot product of x with suppose first b1 first basis element of orthonormal basis. Then if you try to take inner product of x with itself, so decompose x as a linear combination of basis element and take dot product with this one, then it will be further decomposed as, so dot product of alpha 1 times v1 with v1 plus dot product of alpha 2 times v2 with v1. So we know that this will what, so here it will turn at as alpha 1 times inner product of v1 with v1, and we know that v1 is a orthonormal vector. So inner product of v1 with itself would be 1, and 1 time that means remaining alpha 1 into 1. So that means you are getting alpha 1. Similarly, if you want to calculate nth one, so what would be, you will express that you will take out alpha and out, and you will talk about inner product of vn with v1, and here you know that vn is other than v1. So that's where definitely if it is other than v1, then definitely dot product of any two different basis vector of orthonormal basis, what happens? It is 0. So it becomes alpha n times 0. So alpha n times 0 equal to 0. Alpha n times 0 equal to 0. And it says due to property of orthonormal basis. And from here you say that inner product of x with v1, it is giving first coefficient of x or first coordinate of x with respect to a standard basis. So in that process you can say that x you can represent as summation j varies from 1 to n inner product of x with jth element of orthonormal basis vj into vj. So this is the representation. You don't need here, it is very easy to, you even don't have to apply system of linear regression directly. You will get coefficient alpha 1 alpha 2 alpha 3 easily. So this one directly it is talking about coefficient, or you can say that it is talking about coordinate. So that means this coordinate vector of x with respect to orthonormal basis, you can write in a very simple form in term of inner product. That means alpha 1 is what? Inner product of x with v1. Alpha 2 is inner product of x with v2. Likewise, alpha n is what? Inner product of x with vn. So it is all about finding inner product with respect to basis element, orthonormal basis element. So this is the idea. So it looks very simple to easily you can get coordinate of x with respect to orthonormal basis. It is very easy to get. But if it is not orthonormal basis, it is other than any other non-standard basis, then you have to apply system of linear equation. That means you have to solve this one. So in case of orthonormal basis, you don't have to. This solution process is very simple. It is just equivalent to finding inner product of x with respect to corresponding orthonormal basis. So basis element. So you are getting this representation of x with respect to this orthonormal basis element. Similarly, if you take y, so y notation will take, this is the notation of y, representation of y with respect to orthonormal basis, And if you define dot product of x with y, then remember that here x here we are not getting inner product of xy with respect to it is not defined as xi. It is not defined as what we had already seen with respect to standard basis. We had in standard basis we had inner product was defined as summation j varies from 1 to n of xj with yj. What is coming here? We are getting inner product here with it is defined with respect to alpha and beta, alpha j and beta j. So alpha j is what? Alpha j is no more coordinate with respect to a standard basis. Alpha j is coordinate of x with respect to z coordinate of x with respect to a standard basis. So this inner product is defined with respect to a standard. No, this one alpha j is a coordinate of the given vector with respect to orthonormal basis. So this product inner product is defined with respect to a standard basis. Notation has been changed. So this one was what? This notation was meant for inner product of x with y with respect to a standard basis E with respect to a standard basis O, it is different. That means it is all about finding the coordinate. You need to find coordinate vector. If you are able to find coordinate vector of any vector with respect to orthonormal basis, then your then first find coordinate vector, then define inner product with respect to those coordinate vectors. So this inner product is different than this inner product. These two are not equal. Representation look very similar. So one example, after this I will wind up today's class. In next class I will discuss in detail. So a few more properties we can see it here. Like if you suppose this O, it is an orthonormal basis of subspace, k-dimensional subspace V in Rn. Then if you take any vector from Rn, then it would be we will say that this vector x it is orthogonal to the subspace V if and only if x is orthogonal to basis element. Because V is a subspace, so subspace always contains infinitely many elements. So if you are saying that a vector is orthogonal to a given subspace, that means you have to find dot product of that vector with respect to every vector in that subspace. It is not feasible task. So what you do? So what is the feasible task then? What you do in the subspace, we are having a very specific vector. Those vector we are calling it vector basis element. So we get a orthonormal basis and then find the dot product of x with those orthonormal basis. And just if it happens that x is orthogonal, that means orthogonal another name is perpendicular. So I think that idea might be clear to everyone. So orthonormal, you can say that it is perpendicular. Both are same word. Perpendicular. So x is orthogonal to V if and only if x is orthogonal to this basis element. So that is the idea, to find check orthogonality with respect to a subspace. So just I have taken one example. We are taking a plane in R3. Plane means it will have two directions. That means basis of it will have only two elements. So we are taking two vectors which are orthonormal to each other, orthogonal to each other, perpendicular to each other, and having unit norm. And that one is forming a orthonormal basis of this plane V. And if we are taking any element x from R3, then x would be orthogonal to this plane V if and only if x is orthogonal to basis orthonormal basis vector V1 and V2. So this idea from the picture you can see it here. So you are taking x, so you can observe easily see that x is perpendicular to V1. This sign is talking about notation of perpendicular, and x is also perpendicular to V2. So in simply you can say that x is perpendicular to V. Why? Because x is perpendicular to here. From here, this one is saying that x is perpendicular to V1 and x is perpendicular to here. This is talking about x is perpendicular to V2. So that's where X is perpendicular to this subspace B spanned by V1 and V2. And also the angle between these V1 and V2 are perpendicular to each other. So that is the picture, overall picture of representation of any orthogonal factor with respect to a given basis or with respect to a given subspace. So regarding attendance, I have already created a link. Go and mark your attendance there. And in next class,